course, I want to start by thanking the organizers for inviting me to give this talk here. Today I'm going to talk about something that is not my main line of research, but it's rather a project that I did with a PhD student a while ago with Okay, so I think the pointer doesn't work, but no, it doesn't. Okay, so with Vance from the Technical University of Munich. And well, after that, we continued working on something similar for a while. I mean, this project was mostly concerning matrix algebras and Wielandt inequality, so we will see now what this is. And after that, we continued discussing for a while, and we also continued discussing with another PhD student, Yidong Chen from the University of Illinois, Urbana-Champaign. And now we have some new results related to the Lie algebra setting, which I hope will appear on arXiv soonish. This is why I write the 24.0, and then we will see the rest of the reference. And you see that I'm optimistic. I hope that they will appear at most in September. This is why I keep the 0 there, so we will see what happens. But okay, most of the talk will be devoted to the first paper, and then I will just mention a little bit about the second one. It's not only the pointer. Okay, then I guess I will just stay here. No problem. So I will start with the definition of the length of a matrix algebra, and this is actually a very old problem in linear algebra that is called, well, something related to the length of a matrix algebra that is a very old problem in linear algebra that is called path conjecture, and I will tell you now what this is about. So what we are going to do is consider two n-dimensional complex matrices A and B. So I'm going to denote by S the set of A and B. And what we want to do is essentially taking products of A and B, we want to generate the whole matrix algebra. So of course, if we only consider A and B and our matrix algebra has dimension very large, it's not going to be possible to generate it only with A and B, but rather what we are going to do is start taking words in these matrices, so start taking products composed from them. And at some point, when these products are long enough, we will have many different words. So we consider words essentially all these possible combinations of A and B's. And now we are going to consider all possible words on A and B that have length at most L for a certain natural number L, as the set that I'm drawing here. And I'm going to denote it by S less than or equal to L. And of course, one question that we can wonder is, if we are promised that at a certain point we are actually generating the whole matrix algebra, when can we stop? So what is the minimum length such that all words on these two matrices A and B of length at most L span the whole matrix algebra? Okay, this is a very natural question. And as I said, this is a very old problem, and it's actually almost 40 years old. And Paz, who was the first author working on this problem, conjectured that for any generating pair S, for which, I mean, note that here I'm saying generating pairs, so I'm promised that that words on A and B are generating the whole matrix algebra. For any generating pair, the length of words such that all of them until this length generate the whole matrix algebra should be of order of n. So this was the initial conjecture. And what could be proven was what I write here. So first of all, the best bound up to date is due to Shitov from 2019. And what he could prove is that the best bound is of order n log of n, so it has this log of n overhead. And the specific bound 2n minus 2, which is exactly what Paz conjecture, is proven until dimension 6, so you can do it by hand essentially. And then it's also proven in some particular cases. So for example, when you have two matrices that have different eigenvalues, or when one of your two matrices is a rank 1 matrix, or for example, when one of them is a non-derogatory matrix, which means that if you take all the powers of the matrix until n minus 1, then all of them are linearly independent. Okay, so in all these particular cases, the conjecture is actually proven. But, I mean, you might be wondering why I'm talking about this problem here. And the point is that looking at some other problem in quantum information that in principle doesn't have anything to do with this, we realize that actually it's super related to this. And the problem is something that is called quantum valence inequality. So in this particular case, we consider exactly the same. So we consider two n-dimensional complex matrices A and B. And again, we want to generate the whole matrix algebra by taking products on A and B. But now we have one difference, which is that we are only going to consider the words of the same length, of exactly length L. So we are going to take all the products that I'm drawing there. And the question is exactly the same. If we are promised that at some point we are generating the whole matrix algebra, when can we stop? So when do we know that the words on A and B of length exactly L span the whole matrix algebra, right? So it's also a very natural question. And this paper is much more recent, but still it's a bit old, it's almost 15 years old. So what was proven in this paper of Michael Sanz and some co-authors is that for any generating pair S, the conjecture is of order n squared. So in principle, L should be taken of order n squared so that you can stop. And you know that now all the words on A and B of length order n squared are generating the whole matrix algebra. And then, again, I can tell you something about the best bounds that are known for this problem. So again, there were a series of works that were improving each other, as in the case of past conjecture. And among the published papers, the best bound up to date is of order n squared log of n, and it's due to Michalek and Shitov from 2019. And this tells you that for any generating pair, you can always guarantee that you have this. Like for order n squared log of n, you can stop. Apart from this, of course, there were some examples in the original paper of 2010 in which they showed that, well, this order of n squared is pretty reasonable because it's actually something that is fulfilled for these examples. I emphasized in the first point that this was for the best published result because there's an unpublished paper in which it seems that the conjecture has actually been solved. This was a few months ago and it's not peer-reviewed yet, so this is why I'm a bit hesitant, but I think the conjecture should be now solved. And in every case, it should be, well, for every pair of A and B, it should be the case that now you have L of order n squared. Okay, so these are the two initial problems with which I want to start. And of course, as you can imagine, I'm going to focus most on the second one, but we are going to be jumping from both of them from time to time. And of course, here I'm talking about a result that holds for any generating pair, which means that we are always looking for worst case scenarios. But in principle, when we are doing experiments, this is not what we are finding. What we are finding when we do experiments with a computer is a generic case. It's something that happens with probability 1, no? So the question for us is going to be, what can we actually say for these two problems with probability 1? And in this particular case, what we can see is that actually we don't need order of n for past conjecture, or we don't need order of n squared for Wielandt's inequality. We can just stop at order of log of n, which is something that is much shorter, as you can imagine. So this is the main result that I want to discuss now. And well, here, until now, I was a bit hand-waving. Now I'm going to be a bit less hand-wavy, a bit more precise. And for that, we are going to put some math. So first of all, I'm going to define something that we call V generating system and V length. And a generating system and a V generating system are not going to be exactly the same. Because a generating system for me is a pair of matrices for which I have the guarantee that when I take all the products on them until a certain length, all of them together, I'm spanning the whole matrix algebra. And by Vance's theorem, for example, we are promised that we are always, every time that we are adding a new element in the length of our word, we are promised that we are always increasing the space, the dimension of the space that we are spanning until we saturate. However, when we take only the words of a certain length, this is not promised. So in principle, you cannot establish that by going from words of length 4 to words of length 5, you're actually increasing the dimension of the space that you're generating. This is why having a V-generating system and a generating system is not exactly the same. So for me, a V-generating system, as you can imagine, is going to be a pair of matrices, or a set of matrices in this case, for which I'm actually promised that at some point, considering all the words of the same length on these matrices, I'm going to be generating the whole matrix algebra. And what we can see, and it's not difficult to see, is that once it saturates forever. So if for length L we are generating the whole matrix algebra, we can keep adding letters to the word, and we are still going to be generating the whole matrix algebra. Okay, so this is already saturated. So then, of course, the V generating system is what I'm saying here, and the V length is going to be the minimum L for which the words, all the possible words on these letters, are spanning the whole matrix algebra. So this is the natural definition that we have for this concept. And then what we can see is that the V length of any generating system is going to be of order theta log of n for almost all V generating systems. So here there are two subtleties. First of all, when you take a collection of matrices, we are going to see that with probability 1, they are actually a V generating system. And then secondly, we are going to see that with probability 1, you can stop at length log of n. And then of course, if you can stop at length log of n for taking all the matrices of the same length, then this immediately implies the other result, the result of all the words until that length, because of course there you would only be adding more possible dimensions in the space that you're generating. No? So essentially you're already knowing that you have saturated. Okay, so this is the main result. And what I'm going to do now is sketch the proof. So the proof, as we do it, is very, very simple. But actually, because we are hiding that the main technicality of the proof was already done in a previous paper of other authors, for which we didn't have to do anything, of course. But here we only had to reinterpret it. And essentially, the proof can be summarized in the diagram that I'm writing here. First of all, the result holds for any collection of matrices. But for simplicity, we are going to restrict to the case in which we have only two matrices, A and B. And now we are going to go step by step. So the first thing is that here I'm talking about, I think you see the cursor, yeah. Here I'm talking about theta of log of n and no O of log of n. And the reason for that is that we can have both an upper bound and a lower bound to the length, and we are going to see that they match. And this is why we have a theta, no? And the reason to see that is that, well, it's a counting argument essentially, no? So if we consider n words of length L in these two matrices A and B, and now we take all the possible products, as the one that I'm writing here, then it's very easy to see that L has to be at least of order log of n. And the reason for that is that if we count now how many words we can generate with combinations of this form, what we can do is essentially put in any entry of the word, we can put an A or a B, which means that we can generate at most 2 to the L words. And then, since we need at least n squared words to generate the whole matrix algebra, this is very stupid, but that means that we need 2 to the L to be larger than or equal to n squared, no? And then, of course, from here we can solve this, and we can see that L necessarily has to be lower bounded by something of order log of n, and therefore this is why we need at least a length of order log of n so that we are able to generate everything, okay? So this is just a very simple counting argument. And then for the upper bound, which is the interesting part, we follow a few tricks, which are not very deep, but I want to mention them here because they are actually pretty general, so it's something that can be used in many other contexts. And the idea is the following. So you consider a word, like the one that I'm drawing here, for example, the ABBA, and now, for simplicity, let's assign it some decimal number so that we can really put an order in the words. So if we assign a 0 to A and a 1 to B, then we can write ABBA as 0110, which means that this binary number corresponds to 6 in the decimal case. And this means that this word for us is going to be like x6, for example. This is just to put a certain order, no? And then we write the coefficients of the matrix as I'm writing them here. So we are just indexing them, all of them, like x to the 6, sub 1, 1 to 1n, and so on and so forth. So this is just so that we have a way of counting. And now we have this. What we can realize is that each of these matrices is of dimension n squared, which means that the number of coefficients that we have in each of the matrices is n squared. So we have n squared possible coefficients. So what we do in the second step is to write all these matrices as vectors and write all of them in a huge matrix. So now, if you remember at the beginning, we were considering n squared different matrices. So now we take all of them in the first step. We write them like this, and then we represent them as vectors, and we write them in these vertical columns of this matrix. So now we are generating a matrix W that is going to have n squared times n squared coefficients, where all these coefficients are going to be the coefficients of my n squared initial words. Okay, so until here, I'm essentially not doing anything. And now, remember that what we are trying to do is generate the whole matrix algebra. And of course, if we are trying to generate the whole matrix algebra, we need our matrices to be linearly independent, which means that the vectors that we have just created need to be linearly independent, which means that we need the determinant of the matrix that I just created to be non-zero. So if the determinant of the matrix that I just created is non-zero, then all the vectors are linearly independent, and then we are happy. We are good to go, no? We are already generating the whole matrix algebra. And in a bit more detail, if we now put coefficients in the initial A and B, remember that we are taking all the elements X, so all these words, we are taking them as products of A's and B's, which means that all the coefficients that appear here, so all these X with subindices and superindices, are going to be combinations of AIs, AIJs and BKLs. So they are going to be combinations of the coefficients of A and the coefficients of B. So in general, when we compute the determinant of this matrix W, what we are doing is taking a combination of +1s and -1s of a bunch of monomials, all in these coefficients of these matrices A and B. So this is a huge polynomial on all these coefficients, on all these coefficients A's and B's. And now, of course, if the determinant of our matrix is non-zero, which is what we are looking for, this means that the polynomial is not identically zero. And if the polynomial is not identically zero, well, it's a polynomial, which means that the set of zeros of the polynomial is going to have measure zero. So that's why the span of all the columns that I was mentioning before, which were the vectorization for initial matrices, or for initial words, this is going to span the whole matrix algebra almost surely, right? Because the cases in which it wouldn't span have measure zero. Okay, so this is the idea of the proof. There's really nothing there. The only thing that we have to prove is that the polynomial is not identically zero. This is the only thing that is left to be done. And then, this is the part that is actually more difficult. And the trick to prove that the polynomial is not identically zero is that since all the monomials that appear here appear with +1s and -1s, if you can find a monomial that appears only once, then you're done, because it's impossible that it cancels anything else, right? And this is what they did in this previous paper of Klepp and Spenko. They found that actually the monomial that appears, if you take with this order the first n² words that you can construct, the monomial that appears in the diagonal of this matrix appears only once. They did this by some argument well, related to graph theory. And then because of that, because of this monomial appearing only once, you know that nothing is going to be able to annihilate it. So your polynomial is not going to be able to be zero. Or in more generality, what they proved is that there are n² words of length of this quantity that I'm writing here, so of order log of n, essentially, such that the polynomial is not the identically zero polynomial. Okay, so this is essentially where all the technicality of the result is hidden. So right, this is the result that I want to present here. And of course, I mean, we are in a conference that is related to quantum information, so the whole point why I'm presenting this result is because it has applications related to quantum information. And I want to mention a few of them here. So the first one of them has to do with the Krauss rank of quantum channels, or I should say better, the permittivity index of quantum channels. So the first thing that we consider here is a quantum channel, so a completely positive and trace-preserving linear map, as all of you are familiar with. And then what we can do is define what a primitive quantum channel means and what the index of permittivity means. So we say that the channel is primitive if there is an integer such that when we apply the channel these times, so if there's an integer L, such that when we apply the channel L times, and we consider any initial positive semi-definite matrix, the application of this channel L times to it is going to give you something that is positive, strictly positive. Not positive semi-definite, but strictly positive. So this is the interesting thing. The minimum L for which this happens is what is usually called the index of permittivity, and then I'm going to denote it by Q of epsilon. And then in principle, I mean, if I don't tell you anything else from the channel, it would be difficult to see how this relates to the result that I just mentioned before. However, what you can see is, well, first of all, that you can relate this to the Krauss rank of the channel, because if you consider the well-known Choi-Jamilkowski isomorphism, we can construct this matrix associated to the channel. So this is a standard thing in quantum information. And then the rank of the matrix is the frequently called Krauss rank of the channel. And in this paper of 2010, what they showed is that for the channel to be primitive is equivalent to, for the channel to have eventually full Krauss rank. And what does this mean? This means that initially the rank of the channel can be anything, but when you apply it many times, at some point it has full Krauss rank. Sorry. And actually what they further showed is that the index of having eventually full Krauss rank is, so that would be the minimum integer m such that the m-fold application of the channel has full Krauss rank. This is lower bounded by the index of primitivity of the channel. But now, interestingly, if you take the Krauss decomposition of your channel, you can see that you can write it as the expression that I'm writing here. And now, when you apply the channel many times, so if you apply it twice or 3 times or whatever, what you see is that what you're actually doing is adding more on the right and on the left these matrices AIs that I'm writing in the decomposition, right, in the Krauss decomposition, which means that now I'm going to have a huge product of AIs in front of X and the Hermitian conjugates after it. And what I'm saying is that this eventually is going to have full rank, which means that this product eventually is going to generate the whole matrix algebra. So this is why now having full Krauss rank is going to be equivalent to the products of these AIs or AJs spanning the whole matrix algebra. So now we are exactly in the same setting that I was mentioning before, and therefore this means that we have we have full Krauss rank for a certain L if and only if the Wielandt length of the Krauss operators of the channel is exactly L. Okay, so this is how we relate the two settings. So in principle, as a corollary of the results that I was mentioning before, given a generic quantum channel, so again, we are in the context of probability 1, not on the worst case scenario, given a generic quantum channel with Krauss operators given by the set of A1 to AG, the Krauss rank, and therefore the index of primitivity, is of order theta of log of n. However, this is an almost straightforward application of the result that we had before, but it's not completely straightforward because there's one condition for quantum channels that we don't have in general. So for the theorem that I showed you before, we had any collection of matrices, but we were not imposing any restriction on these matrices. However, now for quantum channels, we actually have the imposition that the sum of the AI dagger AI has to be equal to the identity. So it's some sort of normalization on the set of the matrices that we're considering here. So in the initial version of the paper, we had a flaw here, but this remark was made and formalized by Guillaume and Jinbei, and then we could modify the result thanks to that. So this is this is the first application that I wanted to mention. And then the second application will come later. This is kind of related to this application for the moment, and it's in the context of zero error capacity. And I don't want to introduce here what this means. I just want to mention it because Sadvik is going to be talking about this tomorrow. So this is the relation to Sadvik's talk, essentially. So now what I'm doing is considering here a noisy quantum channel. So again, the same framework as before. And then the zero error capacity can be interpreted as the largest quantity such that there is a sequence of increasing length blocks with rates of transmission approaching this length. And the probability of error after decoding everything is 0. So this is a very hand way of explaining it, but Sadvik will explain this much better tomorrow. But the interesting thing here is that in this same paper of 2010, they showed that because of the primitivity of the channel or the non-primitivity of the channel, you have a dichotomic argument always. So either you never go below 1 for this zero error capacity, or at some point this stabilizes at 0. So at some point you hit that the zero error capacity is 0, and this first moment in which you hit this result is the index of primitivity of the channel. And what we can actually see now, thanks to this result, is that with probability 1 you can take the index of primitivity of the channel to be of order theta of log of n, which means that in the dichotomic argument, in the second point, you can stop there at order theta of log of n. Okay, so this was very brief, but also just to put you in some relation with the thing that Salvik is going to mention tomorrow. And now we are going to completely change the gear, and we are going to go to tensor networks. And the second application that I want to mention here is in the context of matrix product states. So I know that many people here are familiar with tensor networks, and a matrix product state is going to be a pure quantum state. Here I'm just writing the dimension in which we are considering this pure quantum state. And what this is doing is essentially modeling a system of L sites. In each one of them, we are associating a G-dimensional Hilbert space. And then what we are going to consider in particular is that this system is, that this pure state is actually translation invariant. And also we are going to consider that we are in a ring, so with periodic boundary conditions. So something like the picture that I drew here. And then we have this canonical form of writing MPSs. So with the expression that I'm writing here. And now you probably see something that starts ringing a bell with respect to the rest of the talk, which is the product of matrices that appears inside the trace, right? In the sum that I'm writing here. So in particular, in this paper in which they started working with these objects in 2006, what they did was to introduce this map, gamma L. I'm not going to talk a lot about the physicality of this map, but essentially what this is doing is bringing some operator from the virtual indices, which are these legs that connect the boxes that I'm drawing here, to the physical indices, which are these vertical legs that I'm drawing here. And now if we consider this map, you see again that you have the trace of any observable x times all the product of these matrices. And what they showed in this paper is that this map is injective if and only if the span of the products of matrices that appear in the argument of the trace spans the whole matrix algebra, which means that we are again in the same business. So this map is injective if and only if the Wielandt length of this set of matrices is upper bounded by capital L, and therefore we can apply again the result here. And what we can say is that given an L such that, L is lower bounded by twice and the seal of log of little g of n, then the map gamma L is injective with probability 1. And this means in particular that if we are given a translation invariant state with periodic boundary conditions, then for this length, what we know is that it's actually the unique ground state associated to a local Hamiltonian that has locality L plus 1, and again, all these things only with probability 1. Well, this was something that's, this is something that is an interesting consequence in the context of matrix product states, but this is maybe not super surprising. So there were already some results in this direction with higher lengths, but still, this was not maybe incredibly surprising. But the interesting thing is that you can actually extend this now to more dimensions. So if you go to the context now of projected entangled pair states, and you consider now lattices in 2D, for example, you can do exactly the same. So now you can generate your map gamma L that brings, again, the virtual indices of the boundary to the physical indices of the bulk, of the PEPS. And then we say that a tensor is normal if there exists a region for which this map is injective. And now for simplicity, what we do is consider regions that are square, just to simplify the calculations. And the minimum side of the lattice such that this map is injective is what we call the index of injectivity. So a natural question now would be, if we assume that the tensor is normal, what is the minimum length such that the gamma of that length is injective? And then this question, of course, is totally analogous to the Wielandt inequality that I was mentioning before, and now this was introduced in 2019 as the tensor version of quantum Wielandt's inequality. And what was shown in this paper of 2019 that I'm mentioning here is that for a given L, the tuples given by the collection of matrices for which the region is not an injective region actually form a Zariski closed of the total space. So that means that in the converse direction, if we have a tensor for which the region is an injective region, then that means that the region is going to be an injective region for almost all possible tensors. I forgot the A there. And that means essentially that it's enough for us to find one tensor for which a region that we construct is injective, and then we are done. And this is what we do. So what we do now is engineer a PEPS for which we can actually show that if the length is large enough, but still of order log of n, then the gamma L is injective with probability 1. And the way to engineer the PEPS is very easy, because we know the result for MPSs, which is in 1D, and now in general PEPS are much more complex because you have your lattice and you have legs in all directions, but you can always construct some canonical case that is called a string bond, which is an overlap between a bunch of MPSs in this direction and a bunch of MPSs in this direction, which is the picture that I draw here. So if you see, in a sense, the dark blues are only going in the vertical direction, and the light blues are only going in the horizontal direction. And by considering this very precise model in which you have injectivity, then you know that you have injectivity for almost all other possible models. So this is why you can also say that now your psi, your PEPS, is going to be the unique ground state of a local Hamiltonian with probability 1. Okay? So with this, I finish the applications of the result in the context of quantum information. And what I want to do is briefly mention the case of Lie algebras. Because of course, I mean, I've been talking about matrix algebras. In principle, there should be some extension to Lie algebras. And what we can naturally do is extend all the notions that I mentioned until now to the context of Lie algebras. And the first thing that we do for that is, well, we consider a Lie algebra G with the commutator, with the Lie bracket, and then we consider a generating system on the Lie algebra. So again, a system for which we are promised that at some point is going to be generating the whole Lie algebra. So in the same way as before, we can define the Lie length as the minimum L, such that our Lie algebra is spanned by this UN. Another way to define the UN is, well, first I take my U, so I define UN, U1 as the span of U, then U2 as the span of U1 and U, and so on and so forth. No? And when we take all these UNs, the first L for which we can stop is going to be the Lie length of the Lie algebra. And in general, this is going to be a bit difficult to explore if we don't impose any other condition. But what we can impose here is that actually all the elements that we are generating are right-nested commutators, for example. And then this is going to be much easier to analyze. So if we do this, then we can analogously define the Lie length as the expression that I'm writing here, which is something that is much more constructive. And the first thing that we did was to wonder, again, what is the minimum Lie length that we need to generate the whole Lie algebra. And what we did was to look at the well-known Lie tree algorithm. And the Lie tree algorithm, what it does is, well, the first thing that would come to your mind. No? So if you are given two words, A and B, and you want to generate the whole Lie algebra, what do? So first of all, you take A and B, then you take the commutator of A and B, then you take the commutator of A with AB and B with AB, and so on and so forth. So what this algorithm does is, at each step, it increases the length by 1, and then it computes a new set of right-nested commutators, and then what it does is take one of them, see if it's linearly independent with the previous ones or not. If it is not, if it's linearly dependent, we discard it. If it's linearly independent, we keep it, and then we continue. And then, of course, the algorithm stops when, at some point, you have at least n squared different elements. No, well, n squared, no, it depends on the Lie algebra. So when it reaches the dimension of the Lie algebra, essentially. So when you use this algorithm, you can do numerics. And this is the first thing that we did. We did numerics because, of course, the problem analytically was much more difficult to deal with. And what we saw was this behavior that I'm drawing there. So, of course, it's not that we could go very far. I mean, we could go only until 20. So this is not super significant. But we did this for random pairs in SUN, and we did this for GL of n, O of n, and so on and so forth. And we saw always that the set of points at which we could stop was always of order log of n. So we started wondering, maybe the same thing that happened for matrix algebras actually happens as well for Lie algebras. And this is what motivated the second paper that we've been working on. So to introduce the results of the second paper, let me go back to the statement of the problem for the B length for matrix algebras, because this is what we've been discussing until now. So if you remember, we were taking all the words of length L, and now, in this case, the Lie length that I was defining was all the words until a certain length. But what we are going to focus on now on for matrix algebras is going to be all words of length exactly L. And this is going to be because for applications is much more useful for us. So again, we are going to ask the same questions that we were asking before for the V length for matrix algebras. And this is going to be, what is the minimum length such that all words of length exactly L span the whole matrix algebra, span the whole Lie algebra, sorry. And what we can see now is, first of all, that as a direct translation between the matrix algebra case and the Lie algebra case, the conjecture that you can write for any finite generating system is of order of the dimension of the Lie algebra. So this is very natural to think. And now again, translating the best bounds that were proven for the matrix algebra case, we can translate them to the Lie algebra case, and we can obtain that the best bound would be of order dimension of the Lie algebra log of the dimension. And the reason for this is essentially that now you can identify the elements that appear in the Lie algebra with an associative matrix algebra by using the adjoint representation. So of course, every time that you do this, if you go from the elements of your Lie algebra to the matrix algebra using this adjoint representation, you increase a lot the elements that are generating your system. And then when you come back to the Lie algebra, you increase even more. So this is why, even though we can prove these best bounds here, we are not super happy because we are always increasing the number of elements in the generating system, and we are still trying to improve this kind of results. However, this is again for the worst case scenario, because this is for the general bounds. But again, in this work, we were interested in the generic case. So what happens almost surely. And for this, we can say a few things in several contexts. The first one of them is in the case of simple Lie algebras. For simple Lie algebras, which are nothing but non-abelian Lie algebras without any non-zero proper ideals, what we can say is the following. Well, first of all, let me say that the two canonical examples of simple Lie algebras are the complex matrices with trace 0 and the skew symmetric matrices. So these two examples that I write here. And then what we can say for simple Lie algebras is essentially that if we consider a generating set of finite cardinality and we consider a simple Lie algebra, then the Lie length of the generating system is going to be of order theta of log of the dimension of the Lie algebra. And the reason why it's theta is because it's already matching the matrix algebra case. And of course, it cannot go better than the matrix algebra case. Because in the Lie algebra case, in particular, if you write down all the commutators of the words as the products that you would obtain from there, you see that it's very easy to find a lower bound for the Lie algebra case in terms of the matrix algebra case. So you can never go better than that. So this is the main result that we obtain for the generic case. And again, we're not super happy because of the number of elements that appear in the generating set. But still, this is for simple Lie algebras. And in principle, if you have a simple Lie algebra and now you put a bunch of simple Lie algebras together, the results should survive. And this is what happens. So if you consider now a semi-simple Lie algebra, you can still do the same. Because again, a semi-simple Lie algebra is a bunch of simple Lie algebras together. So what we consider now is a generating set of finite cardinality of a semi-simple Lie algebra. And then what we can show is that almost surely we have that the Lie length is going to be theta of log of dimension of the Lie algebra. And in particular, if we can write our Lie algebra as a direct sum of these GIs that I write here, then you can even further see that the Lie length of this U, which should be a normal U, is of order of the cardinality of the number of elements that appear in this direct sum, plus the log of the maximum of the dimension of all of them. Okay, so this is to see even a little bit more. But this is not the most interesting thing that you can say because, again, the motivation for this project came from some applications for some particular context in quantum computing in this case. So the most interesting thing that we can actually say for unitary generation or Hamiltonian simulation or all these other contexts has to do with the case in which we are not in the generic setting. Because if we are doing Hamiltonian simulation, for example, and we want to simulate our Hamiltonian with a bunch of gates in a quantum circuit, these gates are very much non-generic, right? Because they are local and then they are tensor with an identity. So this is really not generic. So this is a bit problematic because, of course, this means that all the results that I mentioned before are totally useless in that context. However, what is not so useless is to look at each of these gates separately and at the subalgebra that generates each of these gates separately. So what we can do now is in these boxes that I'm drawing here, in the purple boxes and the pink boxes, we can study all the subalgebras associated to each pair of qubits on this circuit, and then we can merge the results that we obtain for each of these subalgebras separately. So what we do in this particular case is take a 2 to the n qubit setting, like the one that I'm drawing here, and then we consider the set of two local generators given by the Paulis. So we consider essentially the Pauli X and the Pauli sets in individual qubits. So these are the purple boxes that I'm writing here. And then we consider pairs of consecutive qubits. And we consider the products of two consecutive X Paulis and two consecutive set Paulis. And then if we take this as a generating set, what we do now is study each of these U's for each pair of consecutive qubits. And then for each of them, we apply the results that we showed before. And now we merge them carefully, because it's not trivial how to merge them without creating any problem. But now merging them carefully, what we obtain is that actually the Lie length of this generating set everywhere is of order of 2 to the capital N to square. And now if you think about what I was showing you before, you could think, okay, this is really terrible. Because each of these terms here is something that should be considered as in the generic case as before. And for each of them, we had something that was of order log of the dimension. So in principle, patching all these things, you would expect that you get something that is more or less good. But actually, that's not the case. You get something that is pretty bad. So it's 2 to the n squared. So I write here, it is not clear whether this is optimal. I think this is a bit optimistic. I think it's clear that this is not optimal. But what we know is that this is much better than brute force. So if you really try to generate your Hamiltonian by brute force, what you obtain is something that is much, much bigger, because actually this 2 to the n squared is 2 to the log of the dimension of the global Hilbert space to the square, which means that it's much better than what you would have if you only took 2 to the dimension of the Hilbert space. No? So this is why, okay, it's not an amazing result, but it's actually much better than what you would obtain by brute force. And then you can apply this, as I was saying, for some application, for some contexts that have to do with quantum computing. The first one of them has to do with the Lie-Trotter formula. And for the Lie-Trotter formula, which is this expression that I'm writing here, you can actually relate it with the Baker-Campbell-Hausdorff formula, which is this canonical way of expressing the exponential of a sum of two matrices into the products of the exponentials of the matrices. So of course, this is something that you cannot do in general. So what you can show is that the products of the exponentials of the two matrices are equal to the exponential of the sum and then infinitely many commutators. And then, of course, since here you know that when you apply enough of these commutators, at some point you have generated already all of them. What you can know now from this result is that with probability 1, you can stop when you have already nested commutators until length log of n, order of log of n. But of course, this is not constructive. This is a theoretical result that is not going to tell you, even if you stop at this particular point, how to generate all commutators from there on from the previous one. So this is only some constructive result. However, it's much more interesting in the context of quantum neural networks, because if you consider a quantum neural network now defined as a quantum circuit, what you know is that all the layers of these quantum neural networks, and in particular all the gates that appear in the quantum neural network, are going to be constructed by terms of this form, which are given by exponentials like the one that I'm writing here. And then what we are doing now is taking as the generating system the local terms of the Hamiltonian, so this HKs, and we can consider the dynamical Lie algebra associated to this generating set, which is given by the set that I write here. And then, of course, this is this is generated as the union of any possible length of the products of these right-nested commutators of these elements of I, HK. And what they usually do in these kind of papers when they are trying to compute the dynamical Lie algebra associated to a quantum neural network, what they do is to keep simulating these right-nested commutators for a while until at some point they stop. But what we can say now is when you can stop, essentially. So what we can say is that when you have an n of order log of the dimension of the Lie algebra that you're generating here, then you can stop and you have already generated the whole dynamical Lie algebra. So that means essentially that this result can be interpreted as efficiency in the computation of the dynamical Lie algebra for this context. And there are some other applications, but I'm not going to mention them here. So the only thing that I will mention to conclude is that we've been discussing this problem for matrix algebras. That is the minimum length such that all words of length until that generate the whole matrix algebra. And then for any generating system, the conjecture is order of O of n, but the best bound to it is order of O of n log of n. However, in the case in which we consider exactly the length L, the conjecture is order O of n squared, and this is actually proven, or it seems to be proven. And what we say here is that almost surely both lengths can be taken to be of order log of n, and that this has applications in the context of quantum channels, so for the index of primitivity of quantum channels, for matrix product states, and for projected entangled pair states. And then I briefly mentioned how to extend these results to Lie algebras, for which we can essentially say the analogous results. So the conjecture, again, if we consider now commutators of length exactly L, the conjecture would be of order of dimension of the Lie algebra log of the dimension. And almost surely what we can see is that this length can be taken to be of order of log of the dimension of the Lie algebra, even for semi-simple Lie algebras. And in the non-generic case, which is the case that I mentioned for the circuit, the local case is much less efficient, but still is much more efficient than the brute force. So we are still sort of happy with that. And then this has applications in the context of Hamiltonian simulation. So this is essentially everything I wanted to mention. Well, thank you very much for your attention.